Okay guys, so we're continuing the class, and in the previous class, if you remember, I developed the code for the master spring damper, and the only typo that I wrote in the part 20 comments on the YouTube, it was that, I don't know why, because I'm getting older, I forgot to put this transpose here. Now the order of right hand side is 2 by 1. See this transpose, see, I'm just doing this. So please, if you're doing, please do at your code at home. Okay, so now see that so we had the duality principle I taught you. So you have two K. One of the K, as you can see here, this K is for designing the feedback state feedback control law. This KS feedback gain of state feedback. That's right. And we use the Ackermann A, B, and we know this master spring damper, and we assume that the output is only the position of the masses, right? So 1 and 0, and we have like this, and your K we defined by the Ackermann, and then this is state feedback minus K. But as I told in the previous class, your U, okay, you have to use what the real U. In this case we cannot measure the state variable, so that's why we are estimating or observing. So that's minus kx, your state variables M3 and M4. M3 and M4, as you saw in the previous class, look at here, these are the estimated or observed state variables, and this is a x hat, this is x hat, M3 M4, bu plus ke transpose, y minus, this is what, this ke for the estimation. You see that? And I told you that the gain of the estimation ke and gain of the state feedback, they can be completely different gains. You see that here I want to have the desirable eigenvalues of poles of -2 and -2 for the second order system. For the estimation, for gain of the estimation, I have -1 -1. Okay, so please fix this fix this transpose here. So now, hold on. Now if you open this solver, okay, as you can see here, the problem was this. Let me plot it here at for that you refresh your mind, or for those that you don't know what I'm solving. So it was a massive spring damper. This is a spring and the damper, right, and the mass M. So you are applying U, but here in this case, and from the previous class, we assumed that we stretch the mass to this position, non-zero. Based on the code, it is what? It is 0.8. That's right, it is 0.8. Suppose that it is 0.8. Then we're gonna release, but we will apply a control input U. So we want that this go back to 0 and 0 to origin. Here is 0. That's right. 0 and 0, but with this desirable poles eigenvalues. What are those? -2 and -2. This means that you want to have critically damped response. That's right, transient response. But we are estimating because we don't know. That's why I'm giving some random numbers. You see here, these are the real that we are measuring, and these are the observed or the estimated. Because I don't know what is the position and velocity, I'm giving some random numbers. Okay. And you can see, and we plotted U and U. If I run it again, see here, guys. So you see that, let me go to figure 1. So for figure 1 is the X. So this is the real that we see that, and this is the observed, X1E, estimated or observed. Starting from -0.18, that's right. You see that finally your state variable that you want to be X is following the real, so you're estimating the state variable, that's right, or observing. So, and this is velocity that, or is your X2, your second state variable. So this solid blue is for the real, and this is for the estimated, that's right. So, and see that, and this is the control input. The blue and the red is for the estimated control input that we are using. U is equal to -k x hat estimated. That's right. This is estimated UE. See here. So even that, even you change the initial guess, I don't know, to 0.2, say 0.9. I'm changing the estimated initial guess of the velocity of the mass. So if I run it, let us see what you're gonna see. See, that changes everything, that's right. So this time again is going to estimate the state variable. You see exactly what is happening, and see that here is the critically damped system, that's right. And this is velocity starting from 0.9, that's right. See, it's 0.9, and finally follows the state variable, estimating that. And this is the control input to the system. But the red dashed is estimated control input, because you have minus k. Just let me write here. So you have u here is in the state fiat is k x hat, so not x, that's right. So now you can say, you know what, I want to have under damp response. So you're gonna have, so I don't know, say it 5i, a pair of complex conjugate poles, that's right. I'm just magnifying the damp natural frequency to make it visible for you, okay? And this is I. Here we go. So if that's the case, let us see what we get. Yeah, see that oscillations comes up because you have a pair of complex conjugate. So this is the real x1 and x2, and this is observed. So even that the observed or estimated state variable is going to follow your real, that's right. So this is what you have, and this is for the control input, and this is for what? For the velocity dx meter per second. You see that this is under damped behavior, right? So, but first of all, at the home, please type this code, save as MSD. You can just pause it in the YouTube and and you can pause it and type this. That's right. And then you have to pause and type this. I don't upload the blackboard because we are learning. You're on a graduate level, so I want that you type it and learn. Okay, you know, like me, you have some typos, you have to fix it, you have to debug your code. This is how you learn. Okay, and this is for the solver, and you can solve in any name, but MSD, and they have to be in the same folder. So now let us go make it more complex, the problem. Now the problem is that, now suppose this is here and you want to move it here from 0 to some point, So initial guess is 0 and 0, position of velocity, but you cannot again measure the state variable, so you have to estimate that. So you want to follow here. So this is non-zero reference input, that's right. R is, I don't know, 0.4 meter. You want to, this is step input, that's right. You want to move it from here to here. So you have non-zero reference input. So see that, remember I was teaching you, you have R here. R is 0.5, that's right. See, this is the controller. This is your massive spring damper plant and output, that's right. This is plant and this is controller. So as I taught you, let me do it like this. So as I taught you previously, if you remember, we had two approaches. One of them was this. One of them was if you have non-zero reference input that has integrator and without integrator. So you had to modify your control input as minus kx plus ki r, the first element of that k in r, remember? But here, because you're splitting at the same time, you have to put like this. This is one control input for this. And the second that I taught you was minus kx plus ki in zeta. And here we had another term, so you were adding integrator, that's right. And zeta dot, remember that I taught you, was r minus y, which is r minus cx, that's right. Yes. So and the point is that is this x hat, because we cannot measure the gain. Understand? So we are controlling and estimating at the same time. And remember that we had, for the gain, we had this a hat, remember, was original a of the system, 0 minus c 0, and we had b hat, remember, that was b of the system and the 0. And remember that your k of the state feedback must be acre, that's right, acre a hat and b hat and what, and the j. These are our pulse eigenvalues. Understand what I'm talking about? So, and the same can be valid for the KE estimation. Gonna be acre, right? A hat and C hat and the J of estimation. This is J of feedback, that's right. So let me go, because we are, first of all, as homework, I want you go and examine this, only examine this. See that you can move the mass to R of 0.4. See if you can. If you cannot, please make a judgment for yourself why this controller doesn't work. Now I'm gonna try this, the comprehensive. So what I'm gonna do, I have to modify my code. That's right. I taught you have in your notes, okay? So I'm gonna say, see, this is for learning. I hat, I say a hat is equal to your a, which is 0, 1 and 0, that's right, minus k minus c and 0, that's right, and your c minus 1 and 0 and 0. It is clear, that's right? Huh? Let me do it here, because your original c, guys, your original a was like this, 0, 1 based on the code and based on whatever derived in the previous class, minus k minus c, and your c was only position of the mass. So your a hat gonna be 0, 1, 0, minus k minus c 0. This is your a, see here, and your c is minus 0, 0. This is your a hat, and your b originally was 0 and 1, that's right, CISO system, that's right. So your b hat gonna be what, 0, 1, this is b, and 0. Understand? I'm just typing exactly in the Matlab code for this controller that you're adding integrator at the same time you're estimating, that's right. So it's 0, 1, 0 minus k minus 0. So you're gonna have b hat. Okay, b hat is 0, see here, 1 and 0. Now I'm making this comment because I don't need it. Okay, I don't need it. So, and you suppose that I want to make it critically damped. Again, I'm gonna put it as minus 2, that's right. But now you increase the order of the system because this is 3 by 3. You need another thing. So I'm gonna say again minus 2. Make it under damped, that's right, for zeta. So your k acre gonna be a hat, b hat. I'm gonna keep it here, that's right. But your u is, look at here, minus kx, that's right. But because your x, guys, look at here, because your k here is gonna be 1 by 3. Why? Look at the code. Look at the code. Yeah, guys, look at here. I'm gonna, let me show you practically. I'm gonna put a pause here, because you added to order of the system. Look at here, guys. Your k now is 1 by 3. In previous case was 1 by 2, because now you have 3 state variables, that's right. 2 of them is here for x originally, and another is that I'm gonna modify in the code. This is the third one. I taught you already, that's right. So your u, okay, your u gonna be minus k, your x, okay, must be 1 by 3, 3 by 1. So here we go. So here we go. But because this is estimation, but the fourth one is what? Fourth one is fourth one is this gonna be M4, and I'm gonna tell you why. Okay, this is gonna be zeta M3. Okay, plus K of SF 1 and 1 as I taught you here. Look at here, guys. 1 and 1, first element in zeta in M3. I'm going to show you what is M3 because I have to change everything. M3. Please type with me. Okay. M3. Here we go. So because I want to plot it, I'm going to do the same here. See, because I want to plot it. This is for plot, right? Remember from the previous class, this is for plot. Now M3 dm3, this is the equation I'm writing here. This zeta dot r minus y c x hat. Look at here, guys. dm3 is the non-zero reference input. I'm going to define right now minus y, but your y is y hat because is y hat is c, but your c, okay, I'm gonna put c hat because it can be like this, it doesn't matter, but you can increase that also, right? C in what? In estimated M4, M4 and M5. Here we go. This is your what? This is your y hat. That's right. This is estimated output because we don't know. This is estimated output. That's right. Oh, I have it here. Oh, we already have it here. Let me. Why I typed it? See. This is y hat. Estimated output. So this is y hat, right? Based on whatever we have in notes. And now your y for the estimation part, right? For estimation part, your y is c x. That's right. See that this is cx. Hold on, I'm going to teach you. Okay, but the funny thing is your b has order of, look at here, 3 by 1. Your a is 3 by 1, so 3 by 1 cannot be multiplied, 3 by 3 cannot multiply by 2 by 1. So this your x right hand side gonna contain m of estimation, so m of 3, and your b is u, okay, and u, see that u is here, and ke, so you see that what I'm talking about? So see, this is 3 by 3 multiplied by 3 by 1, gonna be 3 by 1. That's right. Actually, you cannot do that. Hold on. I want to make sure I'm doing the right thing. Yeah, we don't need to do that. Okay. Now we have it. So your y is the same, right? And it's y and y hat. You have it here. Understand what I'm talking about? So we change everything, but here because I increased the overall of the system, this is 4 and this is 5. And now see that why I change it. This is x hat is m4 m3, and m3 is for what? For the zeta dot. Then here we go. Okay, why I had to change for the state feedback to these three state variables because your k of the state feedback is the 1 by 3. Understand what I'm talking about? And now we have 5 state variable. I have to increase it to 5. And now 5 state variable, I'm going to say 5. Now the first two, and this must be 0 because I'm moving from 0. So this is 0 state variable, velocity is 0, starting from the origin. I don't know the estimated, you give it a random number, and this is for the zeta. Understand? So I'm gonna have under the critically damped for the feedback control part, and I want to have say critically damped for the gain of the estimation. Understand? So oh, this is estimated, must be 4 and 5, guys. Be careful about this because we increase this to 4 and 5. Okay. Now let me double check the code, make sure everything is right before running. So C is 1 and 0. I don't care it. -2, -2, -2. I can. And GSF. So U is M4, M3. And again is M4 and M5, their estimated position velocity, and M3 is the zeta. Okay, in M3, this is M3 z, this is zeta. Look at here, guys. I'm just implementing this part, right? So K11, and this is the same U. So Y hat, this is estimated output, is CM3 and 4 and CM2, and this is we had already, and this is zeta dot is R minus Y estimated. Look at here, Y estimated. I'm writing here, that's right, and I write here Y estimated. Oh, estimated, I have to increase it to 4 and 5. See, always you have to double check, guys, because estimated is 4 and 5. See, you can make such a stupid mistake and get some ridiculous response. So, and this is, I'm writing here, this is zeta, this is zeta dot, that's right, dot zeta. So real, this is this -1, ANS and JE. Okay, even yeah, that's enough. So it's M15 PU. Now if I run this before teaching at one point, bear with me, I'm not done yet. If I run this, what's happened? Oh, I have pause command. Okay, first of all, I didn't define R. So what is R? R is, as I said, I want to push the mass to point part. This is non-zero set point, that's right. So this is R, and do you have pause? No. Now let me run it to debug it. What's wrong? Oh, I commented. Oh, I commented A and B. I commented A and B. Bear with me, I'm not done yet. So it's interesting that I wanted to push the mass to 0.4. You see that it goes to 0.4, but the estimated doesn't go. Right? Right? Let me zoom in. Okay, but estimated goes to 0.5. Real good. Estimated doesn't go. Means that something is failing in the estimation, guys. So this is the point that I ignored to teach. Now I'm teaching. Okay. So the point is that when you guys, when you are increasing the order of a system, you cannot leave it for the estimation part. So you're gonna have use A hat, and now because A is A by 3, So your C also must be, guys, increased. Your C must be 0, 0, 0 because eliminating by the zeta. So in that case, now this is gonna be M3, right? Because it's gonna eliminate this 0 by M3 gonna eliminate. So here you're gonna have another -1. Understand? So this is gonna be your A hat and C A hat, see, and the C hat. Now your C is this. Understand what I'm talking about? Why is warming up? Hold on. Okay, guys. So sorry. So the thing is that actually it works. So the thing is that now this is M1 and 2, M3. This is 0 for the initial case of the zeta, and because you don't know what is your estimated thing, so I'm gonna put this is for estimated all observed state variables. So if you run this, but you have to be careful, this is 1 and 4 because 1 and 4, 2 and 5. See what I'm talking? So if I run this, right? If I run this, here we go. You see that the mass, the real one, goes to 0.4, and you see that estimated follows the real and goes to 0.4. See, this is non-zero, and this is the velocity, obviously. You see that, and this is the U control inputs exactly they are on each other. See that? So, and this is what it is. Understand? So now you can change it to, I don't know, to -1 plus 3i. You want to have under complete under dam system, -1 minus, say 5i. I'm saying 5i. Here we go, and I keep this as -2. Let's say, and I'm running. See that? I'm making system underdamp, goes to 0.4, non-zero reference input, but both estimated or observed, and the observed, the dashed red is following the real, and the both converge at the same. Understand? But we don't want to have the blue one, so because we're estimating, we need only this red. But I'm just showing here for the comparison. Know what I mean? I'm just showing here for the comparison. Okay, we need the red dashed. Okay, and this is for the U control input. Understand? Now if I even go further, you say I want to go to 0.8, whatever you want. One of the things before running this is that you see that the process of designing K for the state feedback is 3 gains, but here is 2 gains. You can increase it to 3 by saying this is A hat, C hat, B hat, but we don't need that. You know what I mean? We don't need that. So now going to 0.8, we're going to get the same results. Here we go. See? This is your U, this is your X, the velocity, okay? And this is for the position, goes to 0.8, see? 0.8. Understand? So that's it. Now the problem is that I want to make a movie of that. How to do that? I'm saying for K from 1 to 1 to a length of, hold on, to length of what? To length of T, length of T. So what I'm gonna do, I'm gonna say figure number 4, because we are on the figure 3. So plot, or you can say, yeah, plot. Let me do like this, guys. Let me first do it here. This is complete version of designing controller, estimating the unknown state variables, and then making simulation. And we are kind of done with the course, except the next class I'm going to teach you LQR. Okay, suppose guys, here is the I want to plot this square. Okay, you have 4 lines. Here is, suppose here is 0 and is 0, and I want to make it as 0.2. Here is 0.2. This is square. Here's 0 and 0. So here this coordinate of here gonna be 0 and minus 0.2. Coordinate of here gonna be 0.2. Here gonna be 0.2. Oh, sorry, 0.2 and 0. That's right. And minus 0.2 and 0. I'm getting colors. What I'm doing this. So here gonna be 0.2 and 0. Here gonna be minus 0.2 and 0. Here gonna be 0.2 and 0.4. Here gonna be minus 0.2 and 0.4. That's right. Now I'm gonna use the fill command. That's right. But because this is moving, okay, your x is changing, not the y. Your x is changing. So here I'm gonna changing this. Gonna be minus 0.2 plus position of mass. But which position? Estimated. Because if I say y of 1, gonna be true, but we don't know. So this is estimated, that's right. Look at the code. Be wise. We are plotting M4. Here, M4. Okay. Don't say M1. Okay, because we don't know. We are estimating. So M4. Here gonna be this plus 0.2 and y4. The same here. Plus y and 4 here plus y 4. Then I'm gonna use the fill command, but I have to go counterclockwise. This is not random. This point, this point, this point, and this point. So let me write it like that. Okay, I'm gonna say, see here guys, I'm gonna say half of the length HL, half of the length of square is 0.2. For God's sake, I'm just defining. Okay, so this is gonna be, this is fill command. How is it? Fill command. Okay, in the fill you're gonna say, you have to say gives x of f. What was those points? I'm just putting here minus 0.2 plus y4, so it is minus 0.2 plus y of and 4 estimated, predicted. That's right. But because this is a for loop, I have to say not all of them. In each time k. Understand what I'm talking about now? This is one point. Second point is this point, right? Let me show you. See this point, and now this point. Okay. 0.4. Oh, this is wrong, guys. This is plus and 0 again. Why I'm doing that? Always you have to double check your code. Yeah, and exactly is the same. 0.4 and the last quarter of the square minus 2. See, minus 2. So they have the same x. So now the y's of that. This is how we do that. Okay, see, these are the y of f. Y of f for this point was 0, 0. For that point was 2 of h ls, and the same. Right, 2 of HLS. HLF. Now you can come say 0.2 as HLF. I just want to show to HLS, right? HLS, right? Plus minus 0 0 2 point. Okay. Now having that, you're gonna say fill x of f. This is how I write I of f, and what color? Blue color. And you're gonna say hold off. Okay. And then you're gonna say axis, and you're gonna say end. But it's good that you say you have to put the axis. Axis is between minus 0.5 to 0.5, from 0 to 0.5. If you don't do that, you cannot see the movie. Okay, let me first debug it, because I'm human. Let us see what we get. See? Okay, but it's not enough. It says 0.1. Okay, because we want to go to 0.9, guys. So I have to change it to from 0 to 2, and now it must work. And here is, I'm gonna make it as 1.5. Let me see. No. Let me see. Does it working? What? Let me put this. Hold on. Let me fix this, because I'm killing your time. I'm sorry, I had a typo in the code. I doubled the command axis. You see here? Let me show you. See? I don't know why I said axis. This is wrong. See, I had two axes here. I activated that, so this is my fault in coding. So I had a typo. So your axis, oh my god, your axis must be here. See, minus 0.5 to, I don't know, say it 3. Hopefully this now works. Yeah, see? So we started from 0 and finally went to 1, right? You can increase that to make it a score, because it is a score. It looks like it doesn't. I'm gonna say 2.5. See here? Yeah, it is starting from 0 and went to this. Now you can increase that. You can say, I'm gonna go to, we'll make it visible. I'm gonna go to 2.2, go to 2, See, here we go. See, 1 to 2. So you designed an observed state feedback control law that you can plot its, again, guys, we use this, the estimated or the observed for the making the simulation. Understand what I'm talking about? So now please type this, just pausing, and please type this, and now you have what? Please type this, and please type this, the second part of that, and please type this, and now you have the simulation of an observed state feedback control law that you have no access to measure the state variables and so on. So now, if you want to remove the oscillation, I'm just putting this. See, this is now critically damp response. Look at here compared to the previous case. See? That's right. Understand? Here we go. So and obviously you can see, and you can increase the time. Why I'm doing that? And you can say, I wanted to type grid. I typed axis, that's why I was getting error. See? Now it's a grid. Here we go. It goes to 0.2. Understand? So now we are done with everything. Now it's pausing. See that your U finally goes to 0. And this is the dashed red estimated. And it's estimated. So it goes to 0.2. So hold on, I want to just examine this. Okay guys, so now I'm gonna say, you know what, this time I'm gonna make non-zero reference input, but this time I want that my mass moves, okay, moves like as the harmonic force, at harmonic things. That's right. Look at here, I'm gonna increase it to 30 seconds, and here I'm gonna say it minus 2, say 0.5 to 0.5. I want to see that my observed state feedback works well in this case or not. So here we go. See, it's oscillating between whatever is reference input. See, right now based on the observation, right? See, and now look at the graphs. It's coming up. This is my control input. You have some chatting here, but it follows this, right? So see that this is velocity and finally goes here. Pin is 0.4 and 0.4, right? And this is X. I wanted to oscillate between, see that the amplitude of the vibration is 0.3, right? This is 0.3. This is what I get. Okay, here's 0.3. See, 0.3. And let me show you. Almost 0.3. So this is good. That's right. Acceptable things. Now you can make it faster. How? By increasing the frequency. I don't know. Say it. 8T. Huh? Make it. Let's have fun, huh? Let's see. Okay, let us see if it works. See? Why I increase the things and this amplitude decreases, it backs the vibration course. That's right. It's oscillating, but backs the vibration course. See? See what I'm saying? And this is X. What goes to 0 this time. This backs to the frequency ratio that I was talking about in the vibration course. I don't want to teach it here, but this is what it is. Okay. So to resonance frequency. So this is not my for this course. I was teaching the vibration part here for you. So I'm going to say again 0.4. I'm going to say it goes here. So we are done with this course, except that I have to teach you the LQR. LQR, I'm going to work on this code. See, it goes to the 0.4. Here we go. So you can have this for after graduation, this course, this code, and you can extend it to anything that you want. Again, you can increase this to A hat, C hat, B hat, but it doesn't change anything. Okay. So, bye.